All right. So I've got a couple of problems that aren't going to be in the slides. I'm going to do them on paper because it's generally the easiest way to do some of the examples, but I'll get those to you. Yeah, circuits are kind of interesting. It's a lot easier to do them on paper than on screens, I think. Anyway, where we left off, we talked about circuits. We defined Ohm's law, the thing you saw in the lab, the relationship between voltage, current, and resistance. And we defined the power law, which is basically conservation of energy. But it ends up being that the power, right, which is energy per unit time, looks like the voltage, which is energy per unit charge, times the current, which is charge per unit time. So between those things, almost every circuit, every simple circuit can be dealt with. We're not going to apply any other formulas. And then we talked about series circuits. And the idea is that when you add elements to the circuit, so that they're all in one loop, they add to the resistance, which means that the current ends up going down proportional. Right? You apply Ohm's law to the entire circuit, resistance goes up, current goes down. And then we talked a little bit about finding out stuff for each individual component. And each individual component has to hold Ohm's law and the power law. So you can calculate those things. And then we introduced the idea of parallel circuits. The idea is that we have now branching. We have that the current can split in two different places. All right. So where I drew it here in green, all of those conductors are at one potential. They're at 12 volts. And then on the other side, in very dark blue, all of those conductors are at 0 volts. So that the difference between them is the battery voltage. So what happens is current flows through the circuit, and the current leaves the battery, gets to this junction here, and it splits. Part of it goes one way, part of it goes the other. And then at this junction, it comes back together. All right, and that's going to be important later on. We're going to set up some rules. What happens at branches, what happens on loops. But the idea is that this is effectively two circuits. There's the battery and one resistor, right? This loop, let's say, and then there's another loop. And I realize I'm drawing an awful lot of stuff here that's extra. Right. So the gist of it is when we have stuff in parallel, the voltage doesn't really change over the parallel bit. What happens is that the current splits, right? But you can identify how that current splits based on the resistances, and you can solve the circuits, essentially, solve for one resistor independently of another. But to actually do that solving, generally, what we need to do is have a way to add resistances in parallel. In the lab, you saw when you put bulbs in parallel, the resistance went down because the amount of current leaving the battery went up. And we see that we have to deal with parallel circuits because series circuits would just be weird, right? If we had the TV and the lights in series and then a light bulb went out, you'd be sitting in the dark not watching TV. Or if you turned it off, turn the TV off, then the light bulbs would go out. So the real world has lots of parallel wiring. We have to deal with it. And again, we kind of go with this analogy of water flow. Right, your voltage is at like the pressure that a pump provides to push the water through the circuit. And current is the actual flow of the water. Resistance is how hard is it to get the water to go through the pipes. It's hard if you have a long pipe. It is hard if you have a narrow pipe. And if you put in two pipes, it looks like one pipe with a bigger area. And that's what happens when you put in two resistors. It looks like a single resistor where the current's easier to flow, which means it's lower resistance. So when we look at a circuit, what we're going to note is that the current splits. All right, so we can write out the current. The current from the battery equals the current through one resistor plus the current through the other. And we'll apply Ohm's law to that. But in the example that I had, one of these conductors is all at 12 volts. And one of them's at 0 volts. So the same voltage is across each resistor. And so we have a common voltage here that we pull out. And what we get is that the total current is the total voltage divided by the parallel resistance. But these things in the parentheses have to be equal. So we get a rule for how to add resistors in parallel. Now, you probably, if you go look this up, you'll see the rule for two resistors. 1 over R1 plus 1 over R2 is 1 over the parallel resistance. And then they rewrite it, right? They put it over a common denominator. So the parallel resistance looks like R1, R2 over R1 plus R2. You'll see that sometimes, but it doesn't accommodate 3 or more resistors. So it's better to use the thing that I've boxed here instead of, well, that's not what I wanted, but that's fine. Okay. It's better to use this instead of using, another, what looks like a simpler rule. All right, so here is an example. We just have two circuits in parallel. We have a resistor, represents one speaker is 8 ohms, and another speaker is 4 ohms, which you probably shouldn't do that in a real speaker system, but probably doesn't hurt anything. If it's engineered right, it's whatever it is. And so your stereo puts out 6 volts, which is not quite right because it's, it's sound waves, but that's close, Question is to figure out how much current and how much power is delivered to the speakers. Right? And to do that, we have to find the resistance of the speakers. And so we look at this, we realize that they're in parallel, so we're going to do the parallel rule. So the 1 over the parallel resistance is 1 over 4 ohms plus 1 over 8 ohms. Put that on a common denominator that is 3 over 8 ohms. And so the parallel resistance is 8 over 3 ohms, which is 2.67 ohms. And that's what's shown in part A. And then once we have the total, part B is finding the total current. 6 volts divided by this 2.67 ohms is 2.25 amps. So we wanted to find how the current splits. So one way we could do it is to just look at the resistors. One of them is 8 ohms, is twice as resistive as the 4 ohm. So you might naively think that twice the current will go through the 4 ohm resistor as will go through the 8 ohm. And that's exactly right. That is true. So if you can inspect it and say, oh, it obviously divides like that, that's okay. But it's not always clear that that's a way of dividing it. Right? So what you would say is, you have this 2.25 amps, 1/3 of it goes through one and 2/3 goes through the other. But the better way of looking at it is to say, this whole thing here is 6 volts, and this whole thing here is 0 volts. So each resistor has a potential difference of 6 volts. So you can calculate I1 is V over R1 is 6 volts over 8 ohms is 0.75 amps. And then you calculate for I2 is 6 volts over 4 ohms is 1.5 amps. And we go back and we check, does that match our naive assumption? Yeah, I2 is twice as big as I1. And together, 1.5 plus 0.75 adds up to our 2.25. So that's good. All right. So the last thing we need to do is calculate the power across each resistor. And now we have voltage, resistance, and current. So we can do anything. We can do power is voltage times current, or power is current squared times resistance, or power is voltage squared over resistance. Those are all the power law forms. I don't remember what the slides went, so I'm just going to go for it. They used the current and the voltage. And when you calculate that out, the 8 ohm resistor uses 4.5 watts, and the 4 ohm resistor uses 9 watts, which means you have a total of 13.5. And so if you go through and you calculate with the other forms of the power equation, you should get the same numbers. That's a way of checking if your circuit makes sense. If you have a problem, you're working on it, and you're like, it at least tells you, if you go and you check with other forms of the equation, they'll tell you if it's consistent. And consistency usually means it's right. If it's consistent and wrong, then there's something wrong in the problem, in your understanding of it, possibly. So, series and parallel. All right, we have resistors in series. Each resistor has to be on the same wire, the same loop of the circuit. In parallel, they're on different wires. There's a branch. Voltage, the total voltage is the voltage on each one. You add the voltages up. In parallel, they're the same. And then the animations finish going through. For current, the current stays the same through the series resistors. In parallel, it splits up, right? So what you notice here is that the voltage splits and the current splits in parallel. And then the current is the same in series and the voltage is the same All right, so you can remember those. And then finally, the resistance formulas. You add the series resistances normally, just straight addition. And then in parallel, you apply the parallel resistance rule, which I want to say there's a mathematical formula for that. It's like a different sort of average or something. I can't remember what it is. Or maybe it's just, maybe I'm just overthinking it. But you should also check, all right, like let's say R1 here is 50 ohms and R2 is 20 ohms. If you're adding those in series, you have to get a total resistance that's higher. You have to get 70, and 70 is bigger than 50. If you're adding them in parallel, then you have to get a resistance lower than the smallest one, because it's got to be easier for current to flow through the circuit than if you just had the smaller one. So when you calculate this, you would get something probably like 18 and a bit. sorry, 14 and a bit, 14.3. But that's certainly lower than 20. Right, so you should check that your, that your calculations make sense. In parallel, you get a smaller number. In series, you get a larger number. So here we have a diagrammed idea of a more complex circuit. What happens when you add series and parallel circuits together? And this is kind of a, for you in the room, I understand it's a little bit kind of a backed up bit of thing, backed up bit of seeing. So you may want to grab the slides and look over this later. The general thing is when you have a circuit that is complex, that has both series and parallel elements, the way to attack it is to add resistors 2 at a time. And you have to figure out which 2 to add. So if you're looking at the very top circuit, the goal is to get to the equivalent resistance in the bottom right. So starting from the top left, and you start at the battery and you identify resistors, and you'll say, well, I see this 110 ohm resistor. What can I add it to? And I realize I have a choice. And if I have a choice, that means I'll leave it alone and go look at the other ones. Right. So I could add it to the 180, or I could add it to the 220. And that I realize it's parallel there, so I'll leave it. Then I look, I see the 180, it's on its own. I'm going to have to add it to something in parallel. So I leave it, and I look at the other one, 220, I can add to 250. And it's in series, and that makes sense to add those. So I'm going to add those, and I get 470. And then now I can identify these 2 to add. And when I add that, I get a smaller resistance, 130 ohms. And now I see 2 resistors in series, I can add those. So the idea is that you go through the circuit carefully and identify the easiest thing to add up, and you try to add those up. So I'm going to go to the next slide, but I think we're about at the point where I will go through this one. This one's good. And then I'll start doing the worksheet ones. All right, so we want to find the individual voltage and individual current on each resistor. And to do that, we have to figure out what the totals are, right? Figure out, we have a battery, the battery's 12 volts, but we need to find the current. And to get the current, we want to apply Ohm's law to the entire circuit. So we need the total resistance. So we look at this and we say, I need to add some resistors together. And it kind of, the way it's drawn, it kind of makes sense. You're going to add the 2 on the left and then add the 2 on the right. And when you look at it, they're in parallel. And when you see one, you can only really think to add one to the other one in parallel. You can't, for example, you can't do something like add the 6 ohm and the 8 ohm together separately, because it won't make sense. You'll have these other resistors. What it will look like in trying to do it is you have these 2 resistors, but you got something in between them. And you don't know what that is. So when you have something like this, you kind of have to simplify it a little further. You can't just work with that one. So we add those in parallel. We're going to turn all the resistors into the equivalent resistance, and that means doing these 2 chunks. So we do the parallel bits, right? We apply the parallel rule, and note that we're doing subscripts here to identify like which pair of resistors or which group of resistors. Generally, just kind of, as you draw circuits, label them so they make some sense to you. So the left 2 we call R12, the right 2 we call R34. And when we add those, right, 1/4 plus 1/6 looks like 1/2.4. It actually, you calculate it out into some big number over some other bigger number. And this R34 will come out about 3.08. Now you can add those together so you get 5.48. You just add those two in series. So let me pause there. Is that clear, sort of step by step going through? Okay. All right. So now to find the total current, we have one resistor that is the entire circuit and 12 volts. The current's going to be, I is V over R, is 12 volts divided by 5.48 ohms. All right, so we're applying Ohm's law. 12 is I times 5.48 ohms. There should be units here, but these slides didn't like them. So I is 2.19 amps. And now we go and we try to figure out. All right, so we're working backwards, and it's easier to figure out those parallel resistances because we know that if I go back to this slide, we know that these two resistors have the same voltage, delta V12, and these two have delta V34. So we know that 3 and 4 have the same voltage and 1 and 2 have the same voltage. And those two have to add up to the battery to 12 volts. So I'll skip ahead. All right, so we're trying to find a voltage that goes through each parallel branch or across each parallel branch. So we use the parallel resistances. That's why you write down all your work. All right. So you go through those. The voltage is going to be I12 times R12. And so that one is 5.25 volts when you calculate it. And that looks like 2 times 2.5 roughly. So it works out. And then I34 is going to be about 2 times 3. So about 6 volts, 6 3/4. And when you add those two together, you get to 12 volts for the battery. So your math checks out. And now that we have the voltage and current in the parallel bits, now we can go and break it down to the individual resistors. All right. So now we know that this chunk is 5.25 volts, and this chunk is 6.75 volts. And you had some extra numbers there because PowerPoint and the textbook is weird. So, yep. Now you have the voltage and resistance. You can find the current through each one. And there you go. All right, and then all we did here is we took Ohm's law and we very carefully applied it, first to the entire circuit, then to each component as we went through. And then we check, does our answers make sense? Our voltages add up to the battery voltage. And then our current splits, and the current adds up the way it splits appropriately. So I'm going to stop there, and I'm going to stop sharing the slides here. And we're going to try a problem, 2 problems here. All right, so let me pause for a minute and let y'all read on that. This is a reasonable household circuit you might have. And what we're going to do is specify something unusual. We're going to specify power that it uses. Because when you buy a space heater or a microwave oven, they don't tell you that the oven is 80 ohms. They tell you it's 600 watts. They tell you the power it's going to use. You don't care how it's built. But they tell you the power it's going to use, and you know what you're going to plug it into. So we're going to try to figure out the total resistance and the total current for this. All right, because ideally you've plugged this all into a set of outlets on a circuit. You want to make sure that the circuit doesn't use too much current. So you want to check how much you're trying to use when you use all of it. So we have this. Let me get a thing to put under this. I don't want to write directly on. So we can identify that there is a, some number we know for each resistor. In this case, these are powers. And we know the resistance here. And we know that from this conductor is 120 volts, and this conductor is 0 volts. So we know V1 is V2 is V3 is 120 volts. So we can go through and calculate. Now we can calculate the resistance here if we want to from power is V squared over R. Since we got to calculate the total current, we might as well do that as well. As current times voltage. All right, so going through this first one. All right, basically, if you have 2 of the 4 variables, you know you can solve for the other 2 generally. So we have the power is 1500 watts, and we have the voltage is 120 volts. So the current I1 is power over voltage, 1500 watts over 120 volts. And that is 12.5 amps. And that seems reasonable. If you buy a space heater, you expect it to pull a lot of current because it's putting out a lot of energy. So that makes sense. Then I2 is, well, same thing, it's power over voltage. Because we have the power and the voltage. So it's 600 watts over 120 volts, and that is 5 amps. And then we have I3 is, well, now we know the resistance is 10 ohms. So we're just going to do V over R. 120 volts over 10 ohms. So I3 is 12 amps. And so what happens is in the circuit, you have I here, and then it goes I1. The rest of it goes this way, and then it splits here, I2, I3. So I is just adding these up, I1 plus I2 plus I3. And so we do that 12 and a half, 24 and a half, 29.5 amps. So the other part of the problem is to find the total resistance, which means we need to find R1 and R2. So pull this sheet of paper in here for a minute. So the total resistance, we're looking for R1, and well, now we know voltage and current, so we can just apply Ohm's law. V over I1 is 120 volts over I1 here was 12 and a half amps. 120 divided by 12.5 is 9.6 ohms. R2 is V over I2. Same thing, 5 amps. And that should be 24 ohms. And then R3 is 10 ohms. And so now what we have is we have a circuit Instead of squiggles, I'm going to draw boxes because it's just a little bit easier. We have 10 ohms, 24 ohms, and 9.6 ohms. And that is our circuit that goes to our battery. All right, so we're going to add those up. And this is where we do, they're all in parallel. So 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3. And then you go through and you run the calculation. 1 over 9.6 ohms plus 1 over 24 ohms plus 1 over 10 ohms. Right. So 1 over R. So I get that this 1 over R is 0.246, and the units for that is 1 over ohms. Take the inverse. R is 4.07 ohms. And we check, is that smaller than everything? Our circuit was 1 over 9.6, 1 over 24, and 1 over 10. So yeah, it's smaller than everything, so that works. So I have a total resistance. And then it goes completely non-focused. That's fun. All right, does everyone understand? Who's bored out of their minds at this point? Is it kind of, circuits just tend to be a little bit longer and tedious, but the math is straightforward. Understanding what chunk you need to work on is sometimes a little harder. So that was just a straight, everything was in parallel and you had some odd information. What we'd like to do is try a more complex circuit. We have a goal here. We want to find total resistance, the total current, and the information, the voltage and current for the 15 ohm resistor. That's that resistor. And so we have a circuit's battery, 20 volts. We have a parallel branch. We have some stuff in series. So we want to identify stuff that we can add easily and without confusion, all right? When we start going through the circuit, we see, well, here's a 30 ohm resistor. We got to add it to something, and there's two choices. That's kind of messy. And then we go through the 60, we could add with the 15. The 25, we'd want to add with the 60 in parallel. So this is the chunk we got to add up first. And it's in series. So this chunk is 75 ohms. Now we have a circuit that is, this left branch is 75 and the right branch is 25. So we have to add those. So this branch, we're doing 1 over R is 1 over 75 ohms plus 1 over 25 ohms. It's got to be smaller than 25 ohms because it's got to be easier to flow through all of this than just the 25. And so you do that calculation and you'll get that R is 18.75 ohms. Now, what we got is a reasonably simple circuit. You have 30 ohms. You have this equivalent bit. Just add those. So the total is this 30 plus 18 is 48.75 ohms. So we pause there. Step by step, does that make sense to people? And then the other question is, do you think you could identify which thing to start with? So we have a total resistance. Now we apply Ohm's law to find the total current. I is our voltage is 20 volts over 48.75 ohms. And I is 0.41 amps. So we found the total resistance, we found the total current. Now we got to find what's in the 15 ohm resistor. So let me ask a question. Do you know how much current flows through that 15 ohm resistor? The only current we know is the total, is 0.41. So some of my students will say that's what flows through there. Do you know how much flows through the other branch, the 25 ohm resistor then? If all of it flows through one, none of it flows through the other, and that doesn't make sense. The current has to split at this point. There has to be some current go this way and some go this way. So we're trying to find a smaller amount of current. To find how that current flows, then we need to know the voltage on this branch, right? We'll call this I2 and this one I3. All right, so to know how it splits up, we got to figure out essentially how much flows through this resistor and how much flows through these. And to do that, we need to know the voltage in the resistance. So we need to know this voltage. But the only way we could find that voltage is if we knew this one to get how they add up. All right, the idea is we could split this into chunks. Let me get a piece of paper here off to the side. Right, so we have 20 volts is our battery. And then we have something, it's 30 ohms. This has some voltage, we'll call it V1. Then there's the rest of the circuit. So from this point, there's those two resistors, and it comes back. And so this would be V2 and V3. And those two, V1, V2, and V3 have to add up to 20 volts. Or we can keep the circuit going, right? This is 25 ohms. V1 plus V4 has to add up to 20 volts. Is that still readable? Yeah, that's good, I hope. So we're looking for V1 and V4. That's the simplest thing to do. But effectively, however we calculate it, we got to figure out what is going on here. And that's, we know all the current goes through here. So, all right. So V1 is 0.41 amps times 30 ohms. And that is 12.3 volts. So that means that the rest of this circuit from here to here, you know, V2 and V3, well, that equals V4, and that equals 20 volts minus 12.3 volts is 7.7 volts. So now we can figure out how this current divides up. We can figure out the current in the left and the current in the right. So in the right, because one resistor is the easiest thing to go through, I going this way is I3. I3 is 7.7 volts over 25 ohms. And that is 0.31 amps. So that means that this current that flows there, I have 0.31 amps that way and 0.1 amps going through the series resistors, which means the current in the 15 ohm resistor is 0.1 amps, because that's the current that has to go through there. Now you could also try to find this by saying, off to the side here, you could say I2 is 7.7 volts, is the voltage from here to here, divided by that resistance, and 0.1 amps. So now we want this voltage, and that is 0.1 amps times 15 ohms is 1.5 volts. And then the voltage here would be 6 volts. And if you go through and you calculate for every single resistor and you keep the precision I keep, you realize we did some rounding errors. Is that when I do a calculation, there's really like 4 to 6 sig figs. Our accuracy isn't that important. 1 or 2 is fine. So that was that circuit. All right, that was doing that stuff. I should have some solutions somewhere, so I'll try to get those up on D2L. I'm not going to go through all the details of this immediately. I might do it at the end of the class. But the idea is, the question I want to ask out of this is not to calculate everything. Can you identify where to start? All right, what order do we need to add the resistors in? Because that's usually the challenge, is trying to figure out how to add the resistors up. This looks like almost like that circuit that's in the circuits lab homework. There's one resistor missing out of it, and that one didn't have anything labeled. Anyway. All right, where should we start?
45 and 100 ohm resistors.
Why?
Because find total resistance, you're just going to want to eventually set it up so it's basically just adding in series resistors.
Mm-hmm.
So to do that, meaning you can already add one branch in series to get the total resistance in that branch.
Right.
But the other one, you have to find the resistance in those parallel resistors to find the resistance in that branch.
Yeah. That's pretty much it. You can't add the 30 to anything yet. You can add these two. So you could go and just say, hey, these are 75. That's fine. But you can't add this 25 to anything to add in parallel. You have to figure out what these are. So this is probably where you start. Add these, then these two, then these three. So I'm trying to label them. Step 1 would probably be this, and step 2 would be the left and right branch. Step 3 would be the branches in parallel. And then step 4 would be the whole thing. But yeah, doing this problem is essentially the same as doing this problem. We just made it a little more complex. So I don't want to go through all the details of that. I just wanted to lay out what we might want to do. All right. All right, so a few smaller bits that I want to talk about. A lot of what we do when we talk about Ohm's law and power, when we talk about circuits, we talk about idealized circuits, right? And one example where things go wrong is if you've ever had like a light bulb blowout. When you have a resistor, its resistance depends on temperature, and the temperature depends on the energy in the environment there, right? It's radiating, it's conducting, it's convecting energy away. So, whatever it is, it's complex, but it depends on temperature. So that temperature depends on the energy available, which is a function of the current and voltage. So it's complex. And so what happens is on some resistors, it heats up. And so the resistance goes down, more current flows, it heats up, resistance goes down, and it's a feedback loop that eventually burns out the resistor. Light bulb goes. So elements are not ideal, and we pretend they're ideal. One place where we actually have to care about it being not ideal is we talk about current flowing through the battery, and it does. What happens is the electric charge is at one terminal, the negative terminal for electrons. It's going to flow through the circuit, and then it recombines at the other terminal, at the positive terminal for electrons. So inside of the battery, there's a chemical reaction, and it's usually divided into two parts. The part that produces the electrons at the negative terminal and the part that accepts them at the positive. So there's some overall reaction and it's divided. But the gist is somewhere in the battery, ions are moving from one to the other. The material in the battery is changing form as a chemical reaction. And that's not instantaneous. That has a limit, which means the battery acts like it has its own resistance, what's called the internal resistance. And you all have seen this in the lab, is chain together a bunch of, like when you do 3 or more bulbs in parallel. The farther away bulb gets a little dimmer. And if you measured the current in them, it wouldn't be exactly 3 times the current of one bulb from the battery, because you're hitting the limit of how much current the battery can provide. And so it starts acting like a smaller battery, lower potential. Basically, the battery has a little bit of resistance in it, which deducts from the maximum voltage of the battery. So you sometimes have to care about the internal resistance of the batteries. So as an example, you can look at a car battery, has 12 volts, and you can measure the internal resistance various ways. It's about hundredth of an ohm for a good battery. If you draw 10 amps out of the battery, so you're running a pair of headlights, then that small internal resistance is fine. It uses 1/10 of a volt. And so the actual resistance, the actual voltage available to the car would be something like 11.9 volts. But if you're trying to start the car, you're going to use on the order of 100 amps. You might use even more depending on the wiring of your car and what it needs to get the sparks going to start the engine. So for 100 amp demand, that internal resistance has a voltage drop of 1 volt, which means you only have 11 volts available to start the car. you're using up, basically the process of using the battery is not 100% efficient. That's what's going on. You have losses that look like internal resistance and voltage drops. All right, so that's about where I want to stop today, but I am going to introduce the next topic. And the idea is that we have rules that we've been following intuitively, and we're going to state them expressly because they're going to help us to solve more complex circuits. In particular, what happens if we have more than one voltage source? All right, so one rule is what happens when current comes to a branch. And what we've been doing is saying, oh, the current splits. The total current goes in one leg of the branch, and out the other two is smaller amounts of current. Or you could reverse it. You could say current comes together at a branch and the total leaves. And what does this is a conservation of energy or conservation of mass. The electrons can't disappear. So the current that flows in has to flow out of the junction. And so that's the rules. These are called Kirchhoff's rules. The first one is the current rule, which is the total current into a point in the circuit has to equal the current out of that point. Especially a branch, all the current going into a branch has to leave the branch, which means basically, 7 is 5 plus 2, whether it's 7 going into the branch or 5 plus 2 going into the branch. The second rule is treating individual loops of the circuit. So this might be a much more complex circuit, right? This might be, in your car, this might be the headlights, and then you have like the signal lights and the overhead light and the radio and the heater. I mean, the spark plug, the demand for those. But looking at only one part of it, right? The idea is that you start in one part of the circuit, say here. Call that A. And you go around the circuit. All right, so we'll call this point B. We'll call this point C. You add up all the potential differences. So VAB plus VBC plus, and then now we're going C to A. You add them all up in the direction the current flows. That should be starting here and measuring there, VAA, which is 0, because a conductor has a constant potential across it. So when you add up all the potential drops and potential rises, all the batteries, all the resistors, and you add it up, you should get that your total change in potential is 0, which makes sense. If it wasn't 0, then you'd have a wire with some energy on it. That doesn't make sense. So the trick with these things is applying them. And what it ends up being is really, it ends up being linear algebra. You're going to write a bunch of statements that say, you're going to follow the junction rules. Usually says I1 is I2 plus I3. So you get an equation like that. Then you get an equation where you're adding up a bunch of potential differences. And that means you have a system of equations. In this case, 2 equations and 2 unknowns. You solve for the thing you don't know. So applying that to more complex circuits just means you have more equations to solve. But they're solvable and you can do it. And we're not going to give you anything too difficult or too tedious. So that's where I want to stop for the day. That's basically it. If you have homework questions, I'll hang around and do homework questions. But effectively, I think we're pretty much good to go there. Tuesday, we will do all this Kirchhoff rule stuff. And then next Thursday, we'll probably just be like more practice problems. So, any questions, anything? All right, see y'all, bye.
On the homework, there was a question about, it was like 3 different point charges,
Mm-hmm.
and it was asking about the total